This case study examines the practical application of object-oriented programming by designing a command-line notebook application. Our objective is to utilize classes, functions, methods, and docstrings to create a fully functional system. The design process begins with a requirements analysis. We define a note as a short memo that includes the date of creation and searchable tags. The system must allow us to modify these notes and provide a search interface. From an object-oriented perspective, our primary object is the note. To manage all these individual notes, we need a container object called the notebook. While tags and dates could theoretically be distinct objects themselves, for simplicity we'll use Python standard library for dates and simple comma-separated strings for tags. Let's look closer at the note object structure. It contains specific attributes, a memo, tags, a creation date, and a unique integer ID. That ID ensures each note can be precisely selected within a menu. A key design decision here is the inclusion of a match method. It takes a search string and determines if it corresponds to any of the memo or the tags, returning a boolean true or false. By relying on this centralized logic, any future modifications to how we search can be implemented in just one single location without breaking the rest of the system. Moving over to the notebook object, it functions as a controller. It maintains a list of notes as an attribute and includes methods to search, add new notes, and modify existing memos or tags. For user interaction, we are using a menu interface initially, but the notebook class is designed for extensibility, meaning it can easily support graphical or web interfaces later. Finally, let's view the class diagram and project structure at the bottom. In this UML diagram, you can see the menu and command option classes interacting with the notebook class. Notice the line connecting notebook down to the note class with a small asterisk. That indicates a one-to-many relationship, meaning one single notebook contains multiple note objects. To bring this design to life, we need to establish our physical file structure. We'll organize these modules into separate files like notebook.py and menu.py in our next step to ensure proper modularity. Let's look at how we organize our code before writing it to ensure modularity. We are breaking this application into distinct modules. Our executable menu interface lives here in menu.py. The core logic, including the notebook and note objects, goes into notebook.py. We also have command option.py as a placeholder for future interfaces. This separation allows different interfaces to access the core logic without duplicating code. Let's dive into notebook.py, starting with the note class implementation. When we create a new note, the init method takes the memo text and optional tags. It stores them and automatically assigns a creation date using the datetime module. To give every single note a unique identifier, we use this global last_id variable. We start at 0, increment it by 1, and assign it to the new node. Next is the match method, which acts as our search logic. It simply checks if your search string is in the memo or in the tags, returning a boolean true or false. We can test this right in the interpreter. Here on the bottom left, we create two notes. Notice how note 1 gets ID 1 and note 2 gets ID 2. Calling match with the word hello on the first note correctly returns true. Now the notebook class acts as the management layer. Its init method initializes an empty list. The new _note method simplifies adding data. It takes your text, creates the note object for you, and appends it to that self.notes list. For searching, the search method uses an elegant list comprehension. It iterates through all notes and collects only those where the match method returns true. Finally, let's look at refactoring our modification methods. Initially, modifying memos and tags had duplicated search logic.
To follow the don't repeat yourself principle, we extract that into an internal helper method called find_note. The underscore prefix signals to other programmers that this is for internal class use only. It handles the loop to find a note by ID and returns it, reducing our modify methods to just a single clean line of code. So here is the main takeaway. By abstracting repetitive loop logic into dedicated internal helper methods, we make our classes significantly cleaner and easier to maintain. With our core file structure and objects properly implemented, we will next look at how the menu class handles dispatching commands based on user input.
Let's look at how our menu.py file ties everything together. This menu class handles all our user interaction. First, it imports our notebook and note classes that we just organized in our file structure. Inside the initialization method, we set up a dictionary called choices. This is a fantastic Python trick known as command dispatching. Instead of writing a massive, messy block of if-else statements, we simply map string inputs, like the numbers 1, 2, or 3, directly to the methods they should trigger, such as show notes or add note. Next is the run method. It uses a while true loop to continuously display the menu and wait for the user to type something. It grabs the right function from our choices dictionary using the user's input, and if it finds a valid choice, it executes that action. If the action isn't found, it safely prints an error message instead of completely breaking the program. Some of these methods are highly versatile. For instance, the show notes method has a dual purpose. By setting notes equal to none as a default parameter, we can call it without any arguments to show all the notes in our notebook. Or we can pass it a specific list of notes, say the results from a search query, and it will only display those specific ones. Now let's talk about testing and bug fixing. When testing the full application, we discovered two critical bugs related to user input. First, the app crashes entirely if the user types a note ID that doesn't actually exist. Second, we get a data type mismatch crash. This happens because the user's input from the menu comes in as a string, but our underlying note object stores its ID as an integer. How do we fix these? To solve the data type mismatch, we update our findNote method to convert both sides of the comparison to strings. By explicitly checking str of note.id equal to str of noteid, we ensure they always match correctly, regardless of their original type. To handle the non-existent IDs, our modification methods now explicitly check if findNote actually returned a valid note before trying to access its attributes. While this simple check works for now, in the future we will want to use exceptions for much more robust error handling. Wrapping up this case study, let's look at design methodologies. You have two main approaches when building systems. There is top-down design, where you figure out the high-level interactions first and handle the specific details later. This is incredibly useful for object-oriented programming. Alternatively, there is bottom-up design, where you build the small detail components first and then piece them together into a larger system. To practice all of this, your exercise is to build a to-do application. It's structurally similar to our notebook, but adds the complexity of date management. I also want you to experiment with different module import styles, trying both absolute and relative imports to really understand how Python handles code visibility and encapsulation across multiple files. The most important takeaway here is that anticipating invalid user inputs and structuring your classes cleanly is exactly what separates a brittle, crash-prone script from a truly robust professional